for inviting me here to tell you about what we're doing. The title of my talk is called The Next Leap in AI, and that's what I'm going to talk to you about, partly. But I will also, before doing that, I'll tell you where we're leaping from. Because in order to understand what is next, I think it's good to understand what we have already achieved within artificial intelligence and what awesome results have been achieved and which awesome results are still waiting before us. So overall, the challenge in artificial intelligence is to create machines that think, right? Lærke asked us if we thought that machines were going to be able to think. But thinking is actually a meta concept. There's no real strong definition of what it even means to think. So I'll reduce that a little bit and talk about the specific human capability to do what we call cognition. And then I'll talk about what that is and what cognition means and why it gives us humans the ability to do things that no machine has yet been able to do. And then towards the end of the talk, I'll try to present to you what we, particularly at Apsu and together with Trackunit, are trying to do to use a new generation and a completely new way of doing artificial intelligence to make machines that mimic or obtain some of the same results as humans can do through cognition. All right, but first, a little bit about myself. I'm Casper. I'm a partner at a company called Apsu. I'm actually a physicist by background, so that's where the nerdiness comes from. I've been working with simulating artificial intelligence, or actually quantum computing systems, since the late 90s. I've worked a lot with different startup companies, but the overarching thing has always been simulating complex systems, which is now what a lot of people would call artificial intelligence. Currently, I work with a Danish-Spanish startup company called Apsu, where we've collected a group of people who have a special interest in artificial intelligence and kind of the next level of artificial intelligence using supercomputing approaches. We're 16 people in Copenhagen and Barcelona, so it's quite a small company still, only 2 years old. What we're working on is we call it a quantum lattice. I'll return to that a little bit later. A quantum lattice is essentially a quantum-inspired simulation of real systems. In this case, think about we're simulating the brain, but actually a quantum lattice can simulate any real system in nature. And a quantum lattice allows us to accumulate learnings or structure in the perception of reality. So as our quantum lattice is shown data or shown information about the real world, it gets smarter and smarter at solving problems that pertain to that information in a generalized and cognitive way. So that brings me to cognition again. So what is cognition really? Cognition is, and to set the scene for that, I'm going to start by showing how easy it is for humans to apply cognition to a problem. Cognition is essentially when we construct a model or an understanding out of something from thin air. So we don't really have any data. We just have a problem we want to solve, and then out of nothing, out of previous experience, we're able to construct a model on the fly. As a good example, it's actually very easy to trigger human cognition. Just look at this question here. How many red cars are there in Spain? And reflect about that for just a few seconds. What's happening in your head now is actually what's called cognition. You're probably thinking about how could I possibly answer that question. You're drawing on previous experience and understanding of the world, and you come up with some internal model. You probably may also come up with a number. Not really important. The important thing is the process, because you didn't really have any data, right? It's not like you have a big data set that you use to solve that problem. You probably came up with something that's very similar to this, what we call an explanatory graph, a graph that will take you from the question to an answer, maybe applying knowledge or data that you have already stored in your brain, and yield some result. So how many people in the audience thought something like this? Cool. So that's the important part. The important part is that you were able to reason about what could be the path to obtaining an answer to this question. Did you also come up with an answer? Probably not. And that's actually not important, because once you have the structure for achieving the question, it's just a matter of plugging in, seeing what are the actual numbers, or figuring out details like how many people are there in Spain. There happens to be 46 million people in Spain, and so on. Then you have the answer based on very little data. There's 600,000 red cars in Spain. About 12% of all cars in Spain are red. So that's a strong example of human cognition. We were able to do that because we know cars, we know Spain, at least some of us do. We know humans, we know the purpose of having cars, we know they belong to families and they belong to companies. But that's an example of expertise. It's stuff that we have built up in our heads over the years working with the real world. So posing this question, so if I pose this very similar question, how many aerial work platforms are there in Ireland? It's actually interesting to observe, I would not have a clue. I could not construct a causal graph that could lead me from that question to that answer. I have no expertise. I recently discovered what an aerial work platform is. And I do know Ireland, but I don't know how often you use that kind of machine. And I also kind of know what they look like now, an aerial work platform. But basically, I wouldn't know. But a lot of you guys probably do. Right? You probably have an expertise that allows you to construct a graph that's very similar. I haven't tried, that would be embarrassing. But you guys would probably be able to do that. And that's what human expertise is really about. As you work with a field, you gain information about how it works that allows you to apply cognition to solve a problem. So that's how human thinks. That's how a human thinks. That's what we call cognition. So how does a computer think? And that turns out to be very, very different from the way that a human does cognition. So a good example of that is this competition called Imagenet, which is about trying to classify objects that are seen on an image. So these pictures here comes from a collection of 14 million pictures that has been collected and labeled by humans. So each of these pictures, a person has looked at and said, that's a bicycle. There's a lot of data here, a huge data set. And big data is the source of many of the successes we've seen in artificial intelligence recently. So one of the major achievements that has been accomplished over the last say 7 or 8 years in artificial intelligence is in solving problems posed like this. You have a lot of data, and you have a very similar question to ask: what is on this picture? And I think a lot of people was taken by awe when we realized that actual deep neural networks were able to solve this problem with an accuracy that came close to human accuracy. It was able to look at all these 14 million people and accurately learn to say, that's a helicopter, that's a bicycle, that's a woman, with an accuracy of 92-93% achieved in 2012, actually. Since then, progress is slow because some of these pictures can be hard to recognize. But think about that. Did we learn to recognize a bike on a picture by looking at 14 million labeled pictures of things? Probably not, right? I can show you a thing that you've never seen before right now and say, this is a quantum lattice. I unfortunately don't have one. It's a very virtual thing. But if I showed you one and I showed you one again tomorrow, you say, oh, that's one of those quantum lattices that Casper showed me yesterday. And you've only seen one and you never heard about it before. So there's something taking place in a human brain that is not related to big data. Nonetheless, in many situations when you have big data, you can construct things that look kind of like that a convolutional neural network. I think I've lost a slide here. That can solve this problem. But there's something distinctly unhuman about the process, right? We learned it in a weird way by looking at 14 million images, and it also manifests itself in several of the main problems with this approach. So don't get me wrong, I'm really awed by what can be done with deep convolutional neural networks. But this is an example of how unhuman they really are. The pictures on the left column here and there are real pictures from the Imagenet image set. So the convolutional neural networks, state-of-the-art models, were able to accurately classify that as a bus and that as a chicken, I think, a pheasant, actually, and a pyramid. But then applying a small distortion, you're able to trick the convolutional neural network to say, that's an ostrich. That's an ostrich, and that's also an ostrich. And so is that, and that. So in some deep way, an artificial neural network doesn't really understand what it's seeing. I mean, you could never fool a human that way. Philosophers and researchers are debating right now, what does this mean? Can you even say that the network understands the concept of a bus when it thinks that that's an ostrich? Probably not. Doesn't mean it's not useful. It just means that if you have very large sets of data set, you can find statistical correlations that will allow you to predict things that you couldn't otherwise. By the way, where do all these pictures come from? You may have come across things like this. That's an example of how you solicit data in a world where you need huge data sets. The reason a lot of these sites ask us to identify known objects on images is actually because that's being used as a data collection process to train artificial neural networks to identify objects. Just so now you know why you have to answer those questions and what that data is actually being used for. So, this example was an example of artificial neural networks requiring huge sets of data. And that has limited their application to fields where you can collect very big data sets that describe the same kind of problem. And AI researchers have long been aware of the limitation that caused on the use cases where you could apply artificial intelligence, and have been looking for methods to teach a machine to do things without having huge data sets. So just before, the previous speaker mentioned the AlphaGo and the success of DeepMind. Actually, DeepMind first success back in 2012 was when they demonstrated the ability of a reinforcement learning, or agents trained in a simulated environment, to learn to behave in a certain way with no data at all. So that's apparently a very big step forward, right? We don't have to collect 14 million images to teach the system something if we can make it learn by itself by just experiencing something in an environment. A reinforcement learning approach, which is maybe the other and right now the most promising new technology within artificial intelligence, works by putting the AI in a simulator and letting it do the same thing over and over again and learning by experience. So what this was an example of is there are some old games that people my age will know from the Atari age in the late 80s, early 90s, where you were able to play these kind of games on a console. That has been a popular test bed for reinforcement learning models. So you put the robot in a simulated environment where it plays this game and just let it play a million games. And over time, it will actually learn to play. So I'll show you a video of what it looks like as it learns. So this is after 100 episodes, which is actually a lot of games, that it's able to, well, it's starting to realize that the ball can be hit somehow. A little later, yeah, it gets better at this. Sometimes it hits the ball, sometimes it doesn't. Wiggles a little bit back and forth. As you look at this, notice that there's something a little bit unhuman about the way it plays. It still learns, right? But you wouldn't actually do something like that with your stick. But if you're trying to do that in a simulated environment, you may actually learn parts of behavior that doesn't contribute to solving the problem, but is still useful for something. But anyway, after millions of episodes or millions of plays, a lot of episodes, it ended up being really, really good. Actually better than any human player has ever been at playing this specific game. Yeah, so it's discovered this little trick that if you can kick the ball above the wall, it'll just destroy a lot of bricks before it comes down. Clever machine. Has never been shown any data by a human, but it has been allowed to play and play and play again. So this is an interesting next step in artificial intelligence, that you're actually able to solve problems for which you don't have a data set by just letting the computer do trial and error. Of course, that only applies to some situations. There's some situations where it's easy to let the computer learn because the simulation is what you're trying to learn. That's also what led to the AlphaGo. You actually had computers playing against each other. That's what's called adversarial learning. And they become better and better. And no harm done in the millions of cases where they do stupid things. But there are other situations in the real world where it's a little bit hard. For instance, autonomous vehicles. You don't want to have an autonomous vehicle do trial and error learning. You can, of course, do simulated environments where they can experiment with driving a car that isn't real in an environment that isn't real. But then you're limited to the machine learning whatever is there by the inventors, whatever the people who drive the simulation choose to put into the simulation. So there's a long tail problem here. Most car driving actually involves solving problems that you didn't really know that you wanted to solve. Like which simulator designer would think about putting an elephant at the side of the road that could walk onto the street? It never happened to me, but it can happen. That you come I actually once saw a loose elephant in somewhere in the Netherlands. It had run off from a circus. So rare, but it happens. That's what's called the long tail problems. You can't really solve those with that kind of machine learning. Um, and the thing is, even these machines, just like the convolutional neural networks for object detection were stupid in a weird non-human way, so are these. If you take this very same game and you reduce the size of the pad a little bit, the machine just can't play anymore. It just, oops, ball didn't hit. Oh, well, I'll try again, and it just sucks at the game. Problem is, the solution is obvious. To just set it back in the simulator, play another 6 million games, and now it can play with a narrower pad. But it just shows that there's no real cognition, there's no real understanding of what takes place in the machine. Every small change back in the simulator. So if you want to solve a problem like with no data in a simulated environment like that, you have to make sure that you simulate everything that can possibly happen, because there's no innovation on the side of the machine to solve the problem. So, how does APSU deal with this? I showed you the picture of the quantum lattice. The idea in APSU is actually to mimic self-organizing structures in the real world. So we collect small data sets that are related to many different things, like the weather as it evolves, like satellite observations of a certain part of the world, like traffic patterns that we can all feed into the same model and let it learn structures about the relationships between things in a general context. So it's not like the full data set that you apply to an APSU model is actually smaller in any meaningful sense than the data set you apply to for instance, a convolutional neural network. It's just much more diverse. We take data sets that are small in their individual size and apply it to the same quantum lattice, and that quantum lattice over time builds up what is similar to expertise, or the ability to understand what usually drives what, so that the lattice becomes better at coming up with a proper suggestion for an explanatory graph, just like the one with the cars in Spain, than it was before it saw these data. And the more data we show to a certain quantum lattice, the better it becomes. So the data set is fed into the quantum lattice. I won't go into the details. Essentially, you shoot in simulated virtual particles into this lattice, and they pass around, and there's a multiple world aspect here where we try an infinite set of actual pathways through the lattice, and then we find a probabilistic approach to figure out what graphs could be the right graph. But at the end of all that, you're able to extract a graph out of the quantum lattice that is very similar to the graph that I showed you for the red cars in Spain. Yeah. So the core benefits of the approach that APSU has taken to artificial intelligence is that it's a third way. It doesn't work on no data like reinforcement learning, but it doesn't require very big structured data sets either, because you collect information across many similar, but not necessarily exactly the same relationships. So there's a shared learning aspect that the more data you show it about a certain thing, the better it becomes at predicting things that are related to that. That allows you to train models where you don't actually have these huge collected data sets and still get something useful out of the models. And finally, the graph that you get out solves another core problem in artificial intelligence, namely the why of it. In some situations, as a user of artificial intelligence, you're not really interested in why something happens. You're just interested in predicting with a couple of % more accuracy. And in those situations, deep learning can be a good fit. But there are a lot of situations where you actually don't necessarily care so much about getting the accuracy in the prediction. You're more interested in getting an understanding of what drives the processes that you're trying to understand. What drives demand for certain kind of vehicles? What drives delays in certain processes? Not so much that it's going to occur. And in those situations, what you want is really these explanatory graphs. Which brings me back to the red cars in Spain. You weren't able to necessarily compute the number, the 600,000 cars, but you were able to understand that if you added more people in Spain, or more companies, or changed the percentage of cars that were red, you'd get more red cars. And that insight in itself can be a business driver in many situations. So here's an example of how that would work. I'm going to show you a well-known problem based on some Airbnb data, where we know the actual rental contract price for a very large set of apartments across Manhattan. and are able to reliably construct a model that will predict exactly what is the right price to rent out your apartment at. So that data set we fed into a quantum lattice. It came out with a graph that looks something like this: minimum nights, longitude, latitude, room type, neighborhood type, and then it was able to reliably compute the probability or the proper price, the most likely rental price for this specific apartment on Manhattan. So this graph represents the learning. The output can of course be very valuable because it lets you understand what you should set your price at, but just as valuable can be the information that minimum availability has this large of an impact, and the neighborhood, specifically there's like 270 neighborhoods in New York City, and what neighborhoods are actually driving the price for which types of rooms. So the explanatory graph is an important part of what you get out of an APSU model. Also, this is an example of applying it. So we trained the APSU model on this data set, and then we tested on this data set, and this is the actual rate prices, where yellow dots represent more expensive houses, and blue dots represent cheaper rental contracts. Over here we have asked to predict it on a much larger data set, and come up with a model that was able to accurately predict or compute the proper rental price. But hold, this is an example of big data, right? I just said we had thousands of rental episodes, so we were able to train the model. And that's true. But what we then did was that we took a very small set of rental cases in a neighborhood right nearby called Bronx, where it's not that popular to do an Airbnb. So we collected a very small, less than 100 actual rental episodes, and asked APSU to predict what are the proper rental prices for these houses, for these apartments in Bronx, based just on the knowledge you had about Manhattan. And that was this is the litmus test of doing artificial general intelligence. What APSU did in this situation was it looked through the graph on the previous slide, a couple of other graphs that could explain it. It tried to fit this very small data set to it, came up with a new explanatory graph that was similar to the previous one, but had some differences, and it was able to predict the actual contract price for these somewhat larger test set in the Bronx. For the technical-minded people here, I can tell you that the root mean squared error of the prediction of the price was 17, which coincidentally is actually lower than the root mean squared error on the prediction of the houses in Manhattan. So even though we had much less data for the Bronx than for Manhattan, we were able to transfer so much of the information about Manhattan to this new situation that the model actually ended up being even better, which is partially due to the fact that the price fluctuation in Bronx is smaller. So, to finish off this talk, I'll just ask you to imagine what this kind of transfer of information from one situation to another can mean to the construction industry. Where are the situations where we can take a technology like APSU's Q-lattice, show it a lot of data about something that we know in Finland, and let the system take that information and apply it in Sweden or in Texas or in some completely different part of the world to a problem that has commonalities but also differences, but where we have very little data.